In this video, we're going to look at two related topics at the same time. First topic is the idea of instantaneous rate of change, and the second topic is about higher derivatives. So first, let's do a quick recap from one of our previous videos about what the derivative represents. So we'll write the derivative f prime of x, and we can think of that as representing two important things. It can represent the slope of the tangent line to the curve, and it also represents the instantaneous rate of change of our function f of x. So it indicates how quickly our function is increasing or decreasing. So let's look at a couple situations here in this picture. So we've got a curve. Imagine drawing tangent lines at a couple of different points. There we go. So in the left-hand situation here, our tangent line has a positive slope. So since f prime of x represents the slope of the tangent line, we could rephrase that as f prime of x is a positive number. And what that tells us geometrically, if the slope of the tangent line is positive, that means that the curve is increasing. So the y values are getting bigger in this region here as we read from left to right. And then we've got the opposite situation over on the right side. The tangent line has a negative slope. Since f prime of x represents the slope of the tangent line, we could say f prime of x is a negative number. And geometrically, what that means, if we've got a negative slope for the tangent line, it means the y values would be getting smaller as you run along this curve from left to right. So we would phrase that as f of x is decreasing. So we already know that there's this connection between slope of the tangent line and the rate at which the function is increasing or decreasing. And we're going to explore that more in this video. So first thing we'll look at is the idea of motion in a straight line. So imagine that we've got a physical situation where an object can just move in a straight line. So a good example would be a car in a driveway. So this car can move forward and it can reverse. Three quantities that we would want to measure when it comes to this car: displacement, velocity, and acceleration. So for displacement, you often use the symbol S in physics and engineering for displacement. So you could just write S like that, or you could write S of t. When you write something like S of t, then you're just emphasizing, oh, displacement depends on time. It's a function of time. And I get in the habit of using a script S just because otherwise my S looks like a 5. So it's up to you, whether you use this handwriting or that handwriting, really the same thing. You're talking about displacement. So that would be how far has the car traveled from its starting point after t seconds, and we'll be measuring distance in meters. So distance in meters, time in seconds. V of t is going to be velocity. We'll measure that in meters per second. And a of t, acceleration, that's going to be measured in meters per second squared. So again, with these functions, you could just call velocity v, you could just call acceleration a. When we write v of t and a of t, we're just emphasizing that the velocity and acceleration depend on time. So those are three functions that we're going to be interested in as we go through our discussion today. And we can actually bring the derivative into this context when we think about how these different functions are related to one another. So imagine someone gives you a displacement function. They say this is the displacement of the car after any given time. If you then wanted to figure out the velocity, you would say, well, velocity is just the derivative of the displacement. So take the derivative of displacement and you get the velocity. If we say this in words, conceptually what we're saying is that velocity is the instantaneous rate of change of displacement with respect to time. Or more briefly, you could just say velocity is the rate of change of displacement. It's implied in calculus that we're talking about instantaneous rate of change, meaning rate of change at a moment. And we sometimes won't say with respect to time if the context is clear. So velocity is the rate of change of displacement. In a similar way, acceleration is the rate of change of velocity. So you could say a of t is equal to v prime of t. Or if you wanted to even clean up that notation a little bit more, you could say a equals v prime, just to make it more concise. Acceleration is the derivative of velocity. So with that, I think we can jump into a numerical example. So in this example here, we're going to be given a displacement function, and we're just going to do some short calculations related to velocity and acceleration. I think we'll do this on a new page. So here's our displacement function. S of t is equal to t squared plus 5t. In the question, the units are always given just for clarity. So we'll use meters for distance and we'll use seconds for time. Okay, so we would like to find the velocity at 1 second. So how fast is the car going at 1 second? Okay, well, we're going to say v is equal to s prime. So take the derivative of s, we get 2t plus 5. So that gives us a formula for the velocity at any point in time. And then if we want the velocity specifically at 1 second, then we're going to plug the t value 1 into that and we get 7. Always good to give units. So velocity at 1 second, 7 meters per second. Okay, let's try part B. Let's find the time when the velocity is equal to 6 meters per second. So if we had not already found the velocity, then we would do that work. But since we did it in part A, we can just build on that. So we've got this general formula for what the velocity looks like. It's equal to 2t plus 5. And this time we want to solve for the time value. So what we know is that the velocity is equal to 6 meters per second. So we'll plug 6 in for velocity, and then we'll just do a bit of algebra here and find t. So that means 1 equals 2t, or in other words, t equals 1/2. So you could leave that as a fraction, or you might just say t equal 0.5, and that's a time value, so that's seconds. So 0.5 seconds after the car starts moving, it will be moving at 6 meters per second. And let's do one last part here. We'll do something involving acceleration. So part C, let's find the acceleration at time, let's say 1 second. So 1 second after the car starts moving, what is its acceleration? All right, so to find acceleration, we'll say acceleration is the derivative of velocity. And let's look back to part B, where we actually had a formula for the velocity written down. So this is our formula for velocity. So just to be totally clear here, I'm going to say we're going to take the derivative with respect to t of our velocity, and you need to look back to where you had the general formula for the velocity. So it was the 2t plus 5 before we subbed anything in there. So we're going to take the derivative of this with respect to t. So the 2t becomes 2, and the 5 is a constant, so that goes away when we take the derivative. All right, so this is interesting. The acceleration is constant. What that means is that at every moment in time, the acceleration is the same. So there's no t value to plug into. In general, you would have a t value in your acceleration, and then you'd plug in and you'd say, okay, at a certain time, my acceleration is something or other. But because the acceleration is constant here, it doesn't matter what time value you're talking about, you're still just going to get 2. And the units there would be meters per second squared. So now that we've talked about velocity and acceleration a little bit, let's look in detail at the idea of instantaneous velocity, because we probably have a feel for what that represents, but let's look at it in detail, just make sure we're clear on that. So let's start with the idea of average velocity. So suppose that you were measuring, say, a car's average velocity over a certain time interval. So we would say it's the net displacement, meaning how far did it travel over that time interval, and then you would divide by the amount of time in that time interval. So you'd say, okay, it went 70 meters in 3 seconds or whatever to get your average velocity. So then if you sort of just initially think about what instantaneous velocity should represent, you might try something similar. So imagine a car's traveling down the road, freeze time, and you want to know at that moment, at that exact instant, how fast is the car traveling? Well, if you tried this approach of average velocity, you'd say, well, let's look at how far the car traveled over that time interval, and then let's divide by the length of that time interval. Right? So if we did that, we'd say, well, in that instant in which we froze time, the car traveled 0 meters and the time elapsed 0 seconds. So our instantaneous velocity is 0 over 0. So we know that kind of reasoning cannot be correct because we know that the instantaneous velocity is actually defined. We just need to do a little bit more work to think about how to define it. So the trick is we say, well, it doesn't actually make sense to freeze time. What we want to do is look at a very, very, very short time interval. And in calculus, in the language of calculus, you would say, take the limit as the amount of time goes to 0. So look at a very short time interval, then look at an even shorter time interval. Look at this sequence of very short time intervals and let that time go to 0 and figure out the pattern of what's happening there. So we'd still be looking at the net displacement. So where did the car end up versus where did it start? Or where did it end up minus where did it start? And then divide by the length of time. So I'm just going to write t. And we could actually think of that net displacement on top here as, you know, a certain displacement value minus a certain other displacement value. So displacement of where did it end up minus displacement of where did it start. And as soon as we start to write something like this, we realize, oh, that looks like the limit definition of the derivative. And so in fact, the way you get instantaneous velocity is you take the derivative of displacement with respect to time. So this is why limits are so useful. And this is why basically you can't do calculus without the idea of limits, because when you calculate something like an instantaneous velocity without limits, you get 0 over 0. What you need is this idea of taking increasingly short time intervals, looking at the pattern that develops. So figuring out the limit of your function as time goes to 0. And the way we do that is using the derivatives and using all the derivative rules that we built up in our previous section that are all built upon the limit definition. So now we're going to get into sort of the second topic that's contained within this video, which is the idea of higher derivatives. And that's going to allow us to talk about acceleration in a bit more detail. So in this example here, we're going to find all the derivatives of this function. And when we say all the derivatives, we mean we're going to find the usual first derivative, so f prime of x. But then we're going to take the derivative of that. We'll call that the second derivative. We're going to take that, the derivative of that, call that the third derivative, etc. And so you can keep going until you get to 0. And then once you get to 0, once your derivative becomes 0, then nothing interesting is going to happen after that. Okay, so let's say our function f of x is x to the fourth plus 7x squared. Let's take the derivative in the usual way. So we're going to call that f prime of x. And our derivative will look like 4x cubed plus 14x. Okay, now if we want to take the derivative of that, we're going to add a second prime symbol on there. So notice we're adding that second apostrophe, and we just call that f double prime. So f double prime of x, take the derivative of the previous function, it would be 12x squared. In words, you can call this the second derivative. So you can either say the second derivative or you can say f double prime. And you could write that just like that. You don't necessarily need the of x. The of x is just to emphasize what our variable is. So f double prime or f double prime of x or the second derivative. all good ways of naming that function. Okay, so let's say we're really into derivatives and we want to take another derivative here. We're going to get the third derivative. You could write f triple prime of x. At some point, people get tired of writing these apostrophes here, and they get sort of hard to read once you get into 4 or more of them. So another notation is you can just write f with brackets here, where it's sort of in the exponent position. You write brackets and then a 3, and that means third derivative. So take the derivative again, we get 24x. In physics and engineering, it's really the first and second derivatives that you're going to use the most. You will occasionally see, third and fourth derivatives, but in this course, we'll focus mainly on first and second because the theory for the first and second is much richer, and we can basically cover all our topics just using those first two derivatives. Okay, fourth derivative, at this point I would definitely avoid the prime notation. So I would write f, and then in the exponent position just write bracket 4 bracket. That way we know that's the fourth derivative, so that would be 24. And then by the time we get to the fifth derivative, we get 0. So then sixth derivative, seventh derivative, etc. are all going to equal 0 for this particular function. So now that we've seen the idea of higher derivatives, we can revisit our concept of acceleration. So let's go back to this displacement, velocity, acceleration situation. So let's say someone gives you a displacement. And you can say velocity is the derivative of displacement. And now there are two ways of thinking about acceleration. You can say acceleration is the derivative of velocity, but we can now say something new. We can say acceleration is the second derivative of displacement. So if you're given a velocity function and you're trying to figure out the acceleration, then you would say to yourself that acceleration is the derivative of velocity. But if you were given a displacement function, then it would be more natural to say acceleration is the second derivative of displacement. So two ways of thinking about our acceleration. So just to emphasize this, let's do a short example. Let's say someone gives us this displacement function here, s of t is equal to 8t cubed minus 12t squared plus 5, and we're going to find the velocity and the acceleration. So we'd say, okay, well, to find the velocity, we're just going to take the first derivative, 24t squared minus 24t, and then to find acceleration, you can call that a or a of t. Just take the derivative of velocity, so 48t minus 24. So let's talk about the derivative in a little bit more detail, and specifically we want to talk about units that come up when we're taking derivatives. Okay, so we said that velocity is the derivative of displacement, so I would say that's the friendly way to write that. But if we use the d notation for the derivative, we would say velocity, or v, is equal to the derivative of displacement with respect to time. So ds by dt. So the pattern is always d of your function divided by d of your variable. Displacement is our function, time is our variable, so we write ds by dt. This way of writing the derivative is particularly handy when you're trying to figure out what the units are going to be. Okay, so first let's just read this derivative in words. We would say velocity is the rate of change of displacement with respect to time. When we say rate of change, this really means the instantaneous rate of change, meaning the rate of change at a moment as opposed to the rate of change over an interval. And in calculus, we won't always say instantaneous rate of change just because all our rates of change are instantaneous. But I do like to write it down at the beginning of the discussion just to be clear that we are talking about that rate of change at a moment. So velocity is the instantaneous rate of change of displacement. And then you can say with respect to time, if you want to be clear. A lot of the time people wouldn't bother to say that if the context is clear. Okay, so that's just a little literal reading of this ds by dt. So the reason that the d notation is really useful is for figuring out units. See, if we had a problem where we wanted to figure out the units of our derivative, we would look at the units of the function divided by the units of the variable. So you can see from the way that we've written this, we're going to have units of s on top and units of time on the bottom. And so that is rigorously how we know that the units of velocity should be meters per second, because our units for displacement are meters, units for time are seconds. So with velocity, I mean, it's pretty clear from our physical intuition that, or physical knowledge, that velocity is going to be measured in meters per second. But when we run into a new problem, we're going to be able to predict the units using this approach. Just use the d notation for the derivative, and then you can think units of your function divided by units of your variable. So let's try this problem to practice instantaneous rate of change. So we're told that a circular oil spill has radius r and area a. Okay, we could draw a picture of that if we like. So we're talking about an oil spill just on a surface of a body of water, or maybe on the ground. So just two-dimensional. It's in the shape of a circle, and it's got area A, radius little r. So we could pull out a formula from geometry for the area of a circle. We could write A equals pi r squared, and that relates our two variables A and r together. We're going to need that as we go through the problem. Okay, so that takes care of the first sentence. Then the question is to find the instantaneous rate of change of area with respect to radius. Well, whenever you hear instantaneous rate of change, that represents a derivative. So what we're saying is we want to find the derivative of area with respect to radius. So in symbols, two ways to write that derivative. You could write a prime of r, or you could write dA by dr. Either way, we're talking about the instantaneous rate of change of our area function with respect to the radius. Okay, so let's go with the d notation, just because we're going to talk units in this problem, and I think it will be more clear using the d notation. So here's our area function. Let's take the derivative in the usual way. So pi is a constant, and we'll just stay out in front. Taking the derivative of r squared, you get 2r. So that's like pi times 2r. We would more naturally write that just as 2 pi r. So 2 pi r, and then let's think units. So on top, we're supposed to have the units of our area, and then on the bottom, we're supposed to have units of radius. Okay, we're told in the question we want that the radius is going to be measured in centimeters. So given that radius is in centimeters, area is then going to be in centimeters squared. So our units are going to be centimeters squared per centimeter. All right, now sometimes people will ask, well, should I just cancel centimeters and just reduce this to say centimeters? And I would say it's better not to, because let's think about the physical interpretation. This quantity here is the rate of change of area with respect to radius. So what this is saying is, like, if you make the radius 1 centimeter bigger, how much bigger is the area going to get? Well, it's going to increase by 2 pi r centimeters squared. So you really do want to read this as 2 pi r centimeters squared per centimeter. For every centimeter increase in the radius, you get this much increase in the area. So here's our last problem for this video. A cylinder is heated and expands such that its height is always 3 times its radius. Find the instantaneous rate of change of volume with respect to radius when the radius is equal to 10 centimeters. Okay, well, first let's draw a picture of our cylinder. So here's our cylinder. There we go. And let's think back to geometry, where we may have seen the volume for a cylinder. So easy way to think about the volume of a cylinder, think about the area of a circle and then multiply that circle, the area of that circle, by the height of the cylinder. And that way you'd be capturing all the points inside that cylinder. So volume of a cylinder, pi r squared h. Great. Now this cylinder is special because its height is always 3 times its radius. So that's true at the beginning of the problem, and it's true as this cylinder gets heated and expands. So we're going to replace this h here with a 3r. Height is 3 times the radius. So we actually get a new and improved formula for the volume. It's 3 pi r cubed. Okay, so that's good because now we're in the familiar territory of having a function just defined in terms of a single variable. Now we want to find the instantaneous rate of change of volume with respect to radius. So let's highlight that in the problem. So it's implied that the rate of change is instantaneous. You might just see this written as rate of change of volume with respect to radius. What we're asking for is dv by dr, or you could alternatively write that as v prime of r, either way. So what we need to do is take the derivative of v with respect to r. Okay, the 3 will come down in front. We'll have 9 pi r squared for our derivative. So that tells us how quickly our volume is increasing for any given value of the radius. But we specifically want to do this at the moment when the radius is equal to 10 centimeters. Okay, so we'll go, you can either say v prime of 10, or if you were using the d notation, you would say dv by dr evaluated at r equal 10, either way. Whichever notation you prefer. So plugging 10 in here, we get 900 pi. Okay, and then as a final step, let's think units. So we know from the problem that radius is being measured in centimeters because we were told the radius value was 10 centimeters. So what we need in terms of the units here, we need the units of our function, so units of volume on top, and we need the units of our variable on the bottom, our variable being the radius. So if radius is measured in centimeters, then volume is going to be centimeters cubed, and we get centimeters cubed per centimeter. So the answer is 900 pi cubic centimeters per centimeter. And again, it's better to leave it like this rather than canceling the centimeters from the top and the bottom, because what this is saying is that at the moment, when the radius is equal to 10 centimeters. So imagine you look at that specific cylinder that's got a radius of 10 centimeters. So at that moment, for every centimeter that you now increase the radius, this is how much increase in volume you're going to get. So that's what we mean by rate of change. For that little bit of change in the radius, you get this much change in the volume. And this specific number depends on the radius. So if you looked at a different moment in time, say where the radius is equal to 5, so a smaller cylinder, see, plugging in a different number would give us a different answer here. So at the moment when the radius is 5, you would get a different amount of increase in volume for a little bit of change in the radius. So that is the physical interpretation of instantaneous rate of change, and we talked about higher derivatives along the way. Thanks for watching.